Hi folks, this is Murphy here doing a video on section 2.1 in AP Stats, describing the location in a distribution, and it's going to be some concepts that we're pretty familiar with already, like we've talked about percentiles before. We did so in a very specific sense, really talking about quartiles mainly, but we're going to be able to broaden that to talk about comparing any given data point to the rest of its distribution in terms of percentiles, and then again in terms of how many standard deviations from the mean it is in the latter half of this video. But for now, just a quick reminder of what percentiles actually are. The pth percentile of a distribution is the value with p% of observations less than or equal to it. And then I put an asterisk to note that this is sometimes defined differently. It's sometimes defined as not being equal to it, which doesn't include the data point. In other words, strictly being less than that amount of data. This ends up not mattering too much because oftentimes we have a large data set or sometimes an infinitely large data set or a hypothetical one. But below is an instance in which it does matter. So if we stick with this definition, less than or equal to it, then we can try to figure out this problem. Below is a distribution of marking period 1 scores in Jenny's stats class. She earned a score of 86 on her test. How does she perform relative to the rest of her class? So we can look at this. We could see how well she did compared to the rest of her class in terms of percentiles. So where is she relative to everyone else? How many of them did she do better than? Or rather, what percent of them did she do better than? Well, we can kind of count backwards and count down from 25 and see that her score was greater than 21 of the 25 observations. So she is greater than or equal to 22 out of the 25 people, which puts her at the 88th percentile. Good job, Jenny. Here again is the goals for this lesson. We're going to find and interpret percentiles of individual data points. We'll look at something called cumulative relative frequency graphs. I know that's a mouthful. Then we'll start talking about z-scores and what happens if I more or less perform a transformation on an entire distribution of values. But first, a little trivia. I don't know if you knew this one, but the youngest inaugurated president of the United States is JFK. And the oldest one out of our 45 is actually Mr. 45, Donald Trump. That's just a little trivia, but if I were to examine the whole distribution of inauguration ages, I end up with this distribution. If I were to clump these into groups of 5, in other words, if I made a histogram where the bar widths were 5, I'd end up with this. And I'm hoping you can look at the frequency column here and kind of get an idea of what the distribution would look like in terms of shape and center. You could probably guess that the center would be around here, and we have some serious symmetry, like 12 and 13 being almost equal, 7's on either side of that, some very low single-digit numbers on either side of that. So we'd have like rough symmetry and unimodal, like bell-shaped symmetry. Good stuff. And if I wanted to look at relative frequency, like what percent of the 45s fall into each of these categories, well, that's the next column. But what then if I want to look at the cumulative frequency? Well, what that would be is, you can see already how this is starting to relate to percentiles. Sorry, that's my dogs jingling behind me with their chains and stuff. The cumulative frequency, the root there being accumulation. So what if I want to know how many are 49 or younger on their inauguration? That would be this category 7 plus the previous categories 2. If I were to go all the way down to 59 or less, that's the sum of the 12, 13, 7, and 2. So as you can see, every row that we go down, we're accumulating up until we get to the last row where we have the one Donald Trump that falls into this category, and he is the 55 out of 55. He would be the 100th percentile in this case. So how do we calculate percentiles? Really, we've thrown words in front of frequency before. We've looked at relative frequency. Here's cumulative. If I take the cumulative relative frequency, it's basically this column next to it, but divided by the total. So here's something that makes sense. The oldest person is at the, or oldest during inauguration, is at the 100th percentile. You can see that it grows every step of the way. Every bar is greater than the previous one. And remember this is kind of the generalized version of like quartiles when we were making box and whisker plots. Like here's Q3, about halfway through this, the 55 to 59 box. This is almost the median between 50 and 54. And if I were to graph these things, I'd end up with a strictly increasing graph. Interestingly, we can kind of look at this graph, the cumulative relative frequency, as like a rate of change. So calci people could probably deduce, as someone did in class, that more or less the derivative of this graph that we're looking at is equal to the relative frequency column, interestingly. So just to make sure that this is actually sinking in and we understand what kind of graph we're looking at, I would suggest you pause the video and try to answer these 3 questions, but for the sake of time, I will carry on. This graph displays the cumulative relative frequency of lengths of phone calls made to the DMV. Probably not these days. Probably a lot longer than these days. But back when this was made, about what percent of calls lasted less than 30 minutes? So what we should be doing is matching the call lengths to here, because we're saying less than, and this is a cumulative relative frequency chart. This tells us what we're looking for is the percentile associated with it, which just around 64, 65%. I forget why I even chose 64 as compared to, 65. But basically what I'm doing is I'm looking for the x-coordinate of this point and matching it with the associated y-coordinate. Whereas on the next question, I'm doing the opposite, about what call length is at the 40th percentile. So I want to find the point that has a y-coordinate of 40, and this point is at the 40th percentile, and then find the x-coordinate, the call length time, that is associated with that. So that gives me 15 minutes. This is about how this lines up. Great. And then if you could answer the next question correctly, this is kind of like a big deal in terms of understanding why this distribution, what this distribution actually is. About what percent of calls lasted between 21 and 24 minutes? Well, here's that section of the graph. I'm hoping you conclude not 60, not 60-ish even, but 0. Remember, this being an accumulation, having not changed or increased, implies that we haven't accumulated any more data points or any more phone calls in between 21 and 24. In other words, it hasn't grown. This means a couple things here. A cumulative relative frequency chart is always going to be increasing or at a very bare minimum, just carrying on straight through horizontally. It's never going to decrease because we're never going to lose accumulation. It's actually contrary to what accumulation means. So keep that in mind and really double check to make sure that you're understanding what you're looking at and what each point and what each difference between points even, what that actually means. Because we're moving on to the next topic. Again, we're going to kind of talk about standardization, maybe talk about something that you can relate to, because these actually are real SAT numbers from last year. But in general, if X is an observation from a distribution that has a known mean and standard deviation, the score X can be standardized. So what does that mean to standardize something? Well, doing that kind of puts things into perspective, and it makes us be able to look at a data point relative to the mean and relative to the spread of that distribution. It's what allows us to, metaphorically, compare apples to oranges. And before I get into an example of that, let's define the term z-score, because the z-score is going to be the result after we standardize something. The way we would calculate this is kind of a big deal. It's one of the first things on your formula sheet that we're talking about this year. Z equals the value minus the mean over the standard deviation. So what this tells us is, if I were to plop any value in here, subtract the mean from it, and then divide by the standard deviation, that tells me how many standard deviations above or below the mean this data point is. So in other words, if I have a z-score of like 3.5, well, that tells me that the data point that I'm dealing with is 3.5 standard deviations above the mean. If I have a z-score of like -1/2, that means that I have a point that is half a standard deviation below the mean. So sign actually matters here. And I'm hoping you can answer this next question in your head at least. What is the z-score of the mean? The answer, hopefully, being an obvious, 0. The mean is 0 standard deviations from itself. And if I were to plug the mean into this formula, I'd get something minus itself divided by something, which the numerator would become 0, so the whole z-score is 0. So again, a useful tool here is that it allows us to compare things that we normally can't compare. The scores of the SAT and ACT math sections are distributed normally. So the mean SAT math score is 530 with a standard deviation of 110. The same thing with the ACT is 21 and 6 respectively. Suppose this made-up kid Harold scored a 640 on the SAT math and 29 on the ACT. Good job, Harold. That's actually really good. But if I want to know which one of these scores is more impressive, it's not immediately obvious, maybe not, unless you could do some quick mental math, because the scaling is different here. One, you would expect to get a score somewhere in the like half a thousand range, and then the other is in the 20s range, maybe high teens or late 20s if you're extraordinary, either in a good or bad way. But if I want to find out which one of these is more impressive, that's more a question of which one of them is significantly better than the mean. Because we know he did better than average on both of these, but it's just a question of how much. So what we want to do, what we can now do using this notion of standardization, is compare z-scores. So let's do that. Notice the subscript too. The z-score for his SAT mark is 1, because 640 is exactly 1 standard deviation above the mean for SATs. The 530 plus the 110 equals 640. And then his his ACT z-score is a little bit better than that, relatively speaking. It's more than 1 standard deviation above the mean. 6 plus 21 would be 27. He got 29, so he did better than 1 standard deviation above the mean. So, good job, Harold. His ACT score is 1 1/3 standard deviation above the mean score, while the SAT one is only 1 standard deviation. Thus, he did better, relatively speaking, on the ACT. Good job. So now we've talked about 2 different ways of looking at position in a distribution. We've talked about percentiles, and now we've talked about standard deviations and means through z-scores. Some instances are going to be better than others. So if I have a normal bell-shaped thing, distribution, the mean and the standard deviation are going to be the better way to go. The symmetry allows us to say that the middle point will be the mean. Because of the symmetry, it'll make it the same as the median. And then standard deviation being defined as typical distance from the mean, that seems like a pretty good indicator. But if that distance from the mean is different on either side, which is to say I don't have symmetry, and even more so if I have like vast asymmetry, like if I have a skew or an outlier, that's probably when we'd want to go with percentiles. And if we were interested in graphing that, I guess we could do histograms and stuff, but if we had only the raw stats, then the 5-number summary and the quartiles would be fine. So a little fun fact about me and American males here. The height of adult American males is normally distributed with a mean of 69.1 inches and a standard deviation of 2.9. So I am about 5'5", a little shorter actually, but I'm rounding to make it nice and flattering. What's the z-score of my height? Interpret it. Well, what we'd want to do is look at this in terms of inches. Actually, you know what? Take a second to pause and try to figure this out on your own, perhaps. But I'm going to roll through this. In inches, this comes out to 65 inches. If I see the z-score of this 65, well, of course it's negative because this is less than the mean. So when I take their difference in this order, I end up getting a negative value. And my z-score is negative 1.41. So what that means, the interpretation of this, is that my height is almost 1.5 standard deviations below the mean height of my demographic. It's probably going to stay that way too. Pretty sure at age 31 I'm done growing. We should also be able to work backwards. So remember earlier on we were able to go from a data point to percentile and then also from a percentile to a data point. Well, the same thing has to be true of z-scores. We need to be able to go fluidly from the actual data point that I give you to the z-score, but then also if we know enough about the distribution, go from a z-score to a raw score too. If I do that, I could basically take the standard deviation formula on the previous page and solve for x. Or you don't even have to solve for x. You could just kind of, you don't have to solve for x in the formula sense. You can just solve for x after plugging all the other ingredients into the equation. And you get that x equals 72 inches. This is the height that would have a z-score of 1.2. This is 1.2 standard deviations above the mean. So that's what what the z-score actually means. So, something new, and the final thing that's going to be on this section is the notion of transforming data, and then asking how does this actually affect the distribution. So you can imagine there'd be some instances in which if I have a set of values, I'd want to do the same thing to all those values. Like if I have a set of measurements in, say, meters, and I want to convert it to feet, what I'd have to do is multiply by the scale factor that goes there. Or in a case that like I find out one of my measuring devices is off or something, if I'm like a scientist, and I know how much it's off by, like if I step on my scale and I find out that it's consistently like 5 pounds over, then all my calculations, in order to get back to where they ought to be, I would have to subtract 5 from all of them. If I'm curving a test or something by adding or subtracting the same amount or multiplying by a scale factor, whatever. There's different situations in which, if I have a set of data, I might want to change all of those values by the same amount. And then the question is, how does that affect the socks of the distribution? So here's an example. Here's my, let's say like guesses is the initial distribution, and here it is on the bottom half of this top graph. We can kind of see the shape it has. We can kind of see it has some outliers and a lot of gaps actually. If I take this distribution and subtract 13 from every value on here, what does that do to it? What does it do to the center and the spread and the shape and the outliers? Or I should say the state of outliers. If I subtract 13 from everything, are the things that were previously outliers still outliers? Well, the center, if I were to add or subtract a constant a, like in this case I subtracted 13, what does that do to the distribution? Well, now the center, however we define it, mean or median or whatever, has also decreased by 13. the spread won't change, the shape won't change, and the number of outliers won't change either. Think about why that is. If I'm taking every value and just subtracting 13 from it, what I'm essentially doing is just taking the whole distribution, picking it up, and then sliding it 13 units left along the x-axis. That's not going to change how spread out it is. It's not going to change its shape or whether or not there's outliers either. So we end up with the same thing here, with everything except for center. By contrast, we have if I were to multiply or divide by some constant b, we'll say. So let's say the top portion here is our initial thing, our initial set of values in meters. And if I were to try to convert that to feet by multiplying by the scale factor of 3.28 feet, well, that would actually do quite a lot to this thing. It certainly spreads it out a lot. It looks like the shape is more or less maintained, just kind of exaggerated. And well, actually, let's take a look. The center would also be multiplied by b, right? The spread would be multiplied by the absolute value of b. Think about what that means. The way we talk about spread, either range or like standard deviation or percentiles or anything like that, if I were to multiply everything here by a negative number, well, let's talk standard deviation probably, because you can imagine sigma being multiplied by a constant. We can't have negative spread. We can't have a negative standard deviation or negative typical distance from the mean. Distance is positive. So even if the constant that I'm multiplying by is negative, our spread will not become negative in return. Instead, it would become the positive version of whatever that negative scale factor would be. The shape, even though it looks more spread out, it really is the same thing. I would just have to kind of adjust the x-axis to compensate. And then also the state of outliers, because whether or not something is an outlier is all relative, really, to the other data points. That wouldn't change either. So kind of try to internalize these two sets of information here. This is really important for data conversion, and in terms of what changes and what doesn't, that differs slightly between the two things. But again, also try to recognize why adding or subtracting, multiplying, dividing by something won't change the shape, and it won't change the state of outliers. In practice, let's say I give you this data set of a readout of 30 temperatures in Celsius, recorded from an outdoor thermometer for a month at the same time each night. You can imagine we're in America. We don't like to talk in Celsius. We want to know Fahrenheit. So what I could do is I could actually just convert every measurement in this distribution into Fahrenheit instead. And here's the formula to convert Celsius to Fahrenheit. I would take the Celsius temperature, multiply by 9/5, and then add 32 to it. However, if I don't have every data point in the distribution, suppose I just have this. I just have the readout. So I can't take that data and then recalculate it. Well, according to what's on the previous page, I actually don't need to, because I could just take the measurements that I have here, the mean and the standard deviation, and then adjust them accordingly. So what's the mean of the data then? Well, the old mean was 8.43 according to this printout, and according to these two combined facts, what happens to the center? I would multiply by the constant, I would add the other constant or subtract. But in this case, I basically just perform this calculation on the mean. And I get that it becomes 47.174 in Fahrenheit. The standard deviation. This is going to trip some people up. Whether they watch this video or not, I bet this is still going to fool some people. With the standard deviation, if I take the 2.27, why can't I do exactly the same thing here? Why can't I plug it in, multiply by 9/5, and add 32? Well, doing so would be half right, but I shouldn't be doing one of those other things. I should only be multiplying by 9/5. Why don't I add 32 to this? Why doesn't the standard deviation increase by 32 as well? Well, because if every data point, if every one of these temperatures, after being multiplied by something, increases by 32 units, does the plus 32 actually change the spread? If everything moves the same number of units right on the x-axis, does that actually make them any further apart? And when you phrase it that way, the obvious answer is no, of course not. So remember that when you're talking about standard deviation, you'd be multiplying by the constant part, but not adding the constant, because adding the same number to every value in a distribution doesn't make them any further apart from each other. There's some additional practice there, but you know what? I think this is enough to call it quits. So thank you for watching.